Next topic, subgroups and cyclic subgroups. So definition of a subgroup: if a subset H of group G is closed under the binary operation star, that means A B belongs to G, A star B belongs to G. That is the closure property, and that means A B belongs to H, then A star B belongs to H. That means H is closed under binary operation of G, and if H be the induced operation from G itself a group and H itself a group, then H is said to be subgroup of G. Then H is said to be subgroup of G. So we denote H subgroup of G by H less than or equal to G. That means this symbol. So this is called H subgroup of. So now I will give you an example. Uh, R plus is a group. This we already know. And Q actually subset of R. Rational numbers is subset of real numbers. And Q plus is also a group under addition. Q is a group under addition. Therefore, Q plus is a subgroup of R plus. Now I will define cyclic subgroup. Let G be a group and A be an element in G. So A is an element in group G. Then H equal to set of 4 A raised to n where n belongs to Z. That means A raised to A square is something like A star A. A raised to n is A star, etc. star A. If uh, if G star is a group, then set of 4 A raised to n where n belongs to Z is a subgroup of G and is the smallest subgroup of G that contains A, and also it is the smallest subgroup of G that is contains A. Every subgroup containing A contains H. Okay. And H is called the cyclic subgroup generated by A. Then H is called the cyclic subgroup generated by A. Next, we define what is cyclic group. A group G is cyclic if there is some element A in G such that A generates G. That means A generates G. That means generate G means, or if A equal to set of 4, H equal to set of 4 A raised to n, where n belongs to G, then this, if this is equal to G, then we say that it's a cyclic group. Group Z4 plus 4 is not is a cyclic group. Sorry, is a cyclic group because Z4 is set of all remainders when a number is integer is divided by n. So the remainder exists. Okay. So this is actually a group, and the elements are 1, 2, 3. So that is 3 plus 2 is actually 6, sorry 5, and 5 when divided by 4 we will get 1. So similarly we can now, if I am taking 1 is set of 4 1 raised to n. So that means 1 raised to n means 1 star 1 star 1 etc. 2 star n. If it is plus 1 plus 1 plus x, so you can write it as n into 1, where n belongs to z. So we will get 1, 1 into 1, 1, 2 into 1, 2, 3, 3 into 1, 3, 4 into 1, when it's divided by 4, it's 0. So that means this is actually Z4. Therefore, it is a cyclic group generated by 1. And also we can check whether 2 generates. 2 is set of for 2n, where n belongs to Z. That is 2. 4, 4 is 0. Again, 6 is again 2 when divided. So this is not equal to Z4. That's not equal to Z4. So 2 doesn't generate. So if we have actually one element, 1 that generates 4, Z4, therefore it's cyclic. If we have at least one element that generates Z4, then it's cyclic, and we can check whether the other elements generate Z4, and we can calculate number of generators. Again, non-example is Klein 4 group. So we define what is Klein 4 group is V4 is E, A, B, C. So 4 elements are there, and A star B equal to C. The star, we define the star in such a way A star C equal to B, C star B equal to A star A equal to E, B star B equal to E, C star C equal to E. So this is the group, and it's abelian, but there is no element A. Where generate A means uh, A, A star A is actually E. Again, A star A cube is actually A star A, which is A square star A, which is E star A, which is A. So every element B is actually BE, and C is actually CE. So there is no element in this group that generates V4. Therefore, it is not a cyclic group. So now I will do few exercise problems. So if star is a binary operation on a set S, and X is an element of S is an idempotent element for star, if X star X equal to X. So what is the idempotent element? X star X equal to X, then we say that X is a idempotent. So our proof that a group has exactly one idempotent element. So let G be a group, a group, then clearly E star E equal to E. That means identity element is E star E is an idempotent element. So identity element is idempotent element. We have to show that there is only one idempotent element. Suppose X belongs to G is idempotent element, then we can write X star X equal to X. Since G is a group, we can find there exists C is a group, there exists X dash, that means inverse of X in G, that is X dash star X must be equal to E. So what we will do is I'm multiplying this with X dash, so we will get X dash star X equal to, on both sides, X star X. So X star X is actually X. Okay, X star X equal to actually X, and here here it is x star x equal to x. Okay, so okay, sorry, here I am multiplying with x dash, that is inverse. So x dash star x equal to, this is identity element, that is E, and also by associativity property x dash star x star x. So x dash star x is E, star x equal to E, then x equal to E. So that means if there is another idempotent element, then that must be equal to the identity element. So this the group has exactly one idempotent element. The next question, show that a group with no proper non-trivial subgroups is cyclic. So first of all, what is non-trivial proper subgroup? H is said to be is non-trivial proper subgroup, non-trivial proper subgroup if H not equal to E. That means it's not a trivial subgroup, and H is not equal to G. H is not the group itself. So any other subgroup is called a proper. So if there is no proper non-trivial subgroups, then we have to show that the group G is cyclic. So let G be a group with no proper non-trivial subgroup. So and so if H equal to E, then then H is cyclic. If H equal to E, then H is cyclic, and that means H is G itself. Suppose G equal to H E, then G is cyclic. Now, if A not equal to E and A belongs to G, then H equal to the cyclic subgroup generated by A belongs to Z. Then this is not equal to set E because A not equal to E. And also showed that this has no proper non-trivial subgroup. So this must be equal to G since G has no proper non-trivial subgroup. Thus we got A generates G, therefore G is cyclic. A generates G, therefore G is cyclic. So next question is, prove that every cyclic group is abelian. So you know how to prove this. Let G be a group. Let G be a cyclic group. Then generated by, so if it is a cyclic group, it's generated by some element A. That is A generates G. So we denote this symbol. A generates G. Okay. Then we have to show that it is abelian. So let x, y belongs to G. Since G is of the form A raised to 1, etc., A square, etc., Therefore, x must be some a raised to k and y must be some a raised to r. Then what is x star y? X star y is a raised to k star a raised to r. This is actually equal to a raised to k plus r. This is equal to a raised to r plus k. This is equal to a raised to r a raised to k. This is equal to y star x. So for any arbitrary x and y, x star y equal to y star x, which implies G is abelian.